Alright, so continuing on with our Lewis structures, we're now going to look at the shapes of the molecules and how we can use the Lewis structures to actually predict, what the molecules are going to look like in three-dimensional space. So to do this, we're going to be using something known as the valence shell electron pair repulsion model, or just more commonly known as VESPER. Okay, so the way we use this is basically we start off by drawing the Lewis structure, so hopefully we know how to do that, and we'll do some more examples in a little bit. And when we're doing this, we're going to be looking at the central atom, because that's what's going to determine what the overall shape of the molecule actually will be. And then once we look at that, we're going to figure out what the steric number of the central atom actually is. And the steric number here is going to be equal to the number of atoms bonded plus the number of lone pairs on the central atom. And just one thing to note here, the double and triple bonds, don't really matter. All that matters is how many things you're bonded to, not how many actual bonds you have. Okay, so that's why I said it doesn't matter if you have a double or a single or a triple, they just count as one. All that really matters is how many things you're actually bonded to, so that's the important stuff right there. And the third part is figuring out, well, what my hybridization actually is. And what hybridization is basically the mixing of sp and possibly d orbitals. All right, so remember, the orbitals are waves, and what we're going to be doing when we're doing these hybridizations are taking linear combinations of those waves to make new orbitals. Okay, so if I have here a steric number, so Sn is just my steric number, that's equal to 2. This is going to be an sp hybridization. If it's 3, it's going to be an sp2. 4, it's going to be an sp3. 5, it's going to be an sp3d. And if it's a 6, it's going to be an sp3d2. All right, and those are the ones that we're just going to worry about for us. Where do these things actually come from? Well, if we just step back and think about when we talked about how many orbitals are actually allowed. Okay, remember, there's only, and I want to write this way, there's one s orbital. And I should write here that there's a max of one s orbital. So there's a max of one s orbital, 3 p orbitals, and 5 d orbitals. So that's why when we're starting off, we're mixing the s and the p, right? Here we're mixing an s and 2 p's. Here we're mixing an s and 3 p's. And now we've maxed out the maximum number of p's we can have, so then we have to start adding the d's. So I have sp3 and then a d, and here's sp3 and 2 d's. All right. Now, you could conceivably keep going with this, but eventually, at this point, with a steric number of 6, you're already bonded to 6 things, and it's getting extremely crowded around the central atom, so you really can't go any further than that. There's a couple of compounds that actually do have steric numbers of like 7 and possibly 8, but those are fairly rare, and we're not going to deal with them in this class here. What we're dealing when we're talking about sp and sp2s and sp3, these hybridization is essentially a mixing of these orbitals. Okay. So if you remember, orbitals are waves, right? It's just, waves in three-dimensional space of electrons and all that. Hybrid orbitals are going to be linear combinations of these hybrid set orbitals. In other words, we saw this earlier, basically if I have my wave function here, and this is going to be my hybrid, this is going to be equal to some summation here from I is equal to 1 to n, where n is just going to be some number 1, 2, 3, 4, 5, 6 possibly, of some weighting coefficients times basis set wave functions. So this is either going to be your S or your P or your D wave functions there. And it's just adding those up, and when you add all these things up, and I should really put there that's going to be I. So it's just going to be adding these things up, and that's going to give you your hybrid orbitals. Here are the linear combinations of the basis set atomic orbitals which make the hybrids. The white and gray portions of the orbitals represent the positive and negative phases of the wave functions. If you add 2 positive portions, the probability increases, which is constructive interference, and if you add a positive and a negative portion, you get smaller probability, which is destructive interference. You notice the hybrid orbitals, there is a large lobe and a much smaller lobe. This is a result of the constructive and destructive interference between the different atomic orbitals. At the top we have the sp hybrids, which are made of a linear combination of the 1s and 1p orbitals in equal amounts. The reason all these factors have square roots in them is because the hybrid orbitals need to be normalized. In other words, the probability, which remember is the wave function squared, that the electron exists in the new orbital must be 100%. Basically, it's just a calculus thing. Next we have the Sp2 hybrids, which are made of the s and p orbitals in different proportions. Notice in the Sp hybrid, the py and pz orbitals aren't used, and the Sp2 hybrid, the py orbital isn't used. This is because the unhybridized orbitals can also be used for double and triple bonds. Next we have the Sp3 hybrids, and these are using all the s and p orbitals. And there's also for the Sp3d and Sp3d2, those also have similar equations as well, but we're not going to bother with them here. Alright, I'm not going to ask you to try to memorize all of this, but hopefully you just have a better understanding of when I'm talking about linear combinations of atomic orbitals now. So when I'm talking about an sp orbital, if we look at something like beryllium. So if here is beryllium, and I have here a 1s orbital, and then I have up here my 2s orbital, then I have my 2p orbitals. Now when I fill this up in its ground state just by itself, that's going to be my electron configuration. Now if we want to undergo bonding, well, there's no open orbitals for my beryllium to share with. So what's going to happen is it's basically going to do a linear combination between the 2s and one of my 2p orbitals. So when I get the hybrid out, well, this 1s down here is not going to be touched. But now I'm going to have here an sp orbital with the remaining 2p orbitals like this. So then, according to Hund's rule, it's going to fill up like this. And now my beryllium has two unpaired electrons, and now if something like fluorine comes along, it can go and share the electrons with those fluorine atoms, and then you can make yourself a nice little molecule. We can also look at something like carbon, for instance. So here's going to be my carbon. Again, there's my 1s. So in my ground state, it looks like this. So carbon right here has two possible open spots here for bonding, but the problem with this is carbon likes to form 4 bonds. Also, these bonds here are at right angles to one another, right? Remember the p orbitals are all 90 degrees, along the x, y, and z axes. So we can't just have, this because this doesn't represent reality at all. So instead what's going to happen is this is going to hybridize with all these, like so, and we're going to get here, my 1s is still alone, and we're going to get 1, 2, 3, 4. So these are the same. And then I have here 4 electrons, so again, according to Hund's rule, go in like this. This is going to be an sp3 orbital, just like that. So that's going to be my hybridization. As you can see right here, it takes, 4 spots, right? If you just look at the steric number here, I have 1s in each one of these, and then that's going to be 1p, so that's 1 plus 1 is 2. Here I have 1 plus 2 p's, that's 3. 1 plus 3 p's, that's 4. 1 plus 3 p's plus a d, that's going to be 5. 1 plus 3 p's and 2 d's, that's a 6. Okay, so really, if you forget, counting the steric number is really easy, but of course, figuring this out is also really easy because, again, the most you can ever have is 3 because there's 3 p orbitals. Then you simply just count up until you get to the number here. You start with your s, then you go to your p, and then eventually your d if you need some more. All right, so really this part right here is quite simple. There's a nice little pattern to it. Don't over think that stuff. All right, now if we go here to nitrogen, so nitrogen, of course, has this electron configuration as an atom. Right. Now, when this bonds, you might say, well, here I have my 3 orbitals, and I have 3 open spots. Why can't I just bond here? Again, remember, this is basically going to experimental data, is that, all the bonds would be predicted to be at approximately 90 degrees relative to one another, which is not observed in real life. So instead, these are going to, again, hybridize like so. And we're going to get... So now these are going to hybridize in this fashion. So this is still going to be an sp3, except right here, this is going to be my lone pairs of electrons. So that's why if you're going to be seeing the nitrogen like this, you're going to have a lone pair of electrons, and then these 3 orbitals are going to be just like this. And of course, here's oxygen. Same thing, here's my 1s, 2s, and then I have my 2p. In its ground state, it looks like this. And again, you might say, well, here I have 2 open spots that can just bond. Again, that would be predicted to have a 90-degree bond angle, which is not observed in real life. So what we're going to have here again is these are just going to hybridize. That's still going to be my 1s, it's left alone, and we're going to get just like that. All right. And again, this is still going to be an sp3 hybrid. All right, because again, if you look at the bond angles for water, it's going to be much closer here to the tetrahedral version than the 90 degrees. okay? And again, these are going to be 2 lone pairs. All right, now I was saying here that, experimentally, we're seeing certain bond angles. So if I just draw here, for instance, methane, and then ammonia, and then of course water. The bond angles, when I'm referring to the bond angle, I'm talking about the hydrogen, carbon, hydrogen, hydrogen, nitrogen, hydrogen, or hydrogen, oxygen, hydrogen. So that's going to be, these angles, and they're going to be equivalent for the different bonds. Well, for methane, and we saw this way back in the organic structure video, that's 109.5 degrees. For ammonia, this is 107 degrees, and for water, this is 104.5 degrees. So you can see that these are all pretty close to one another, right? As opposed to our initial prediction up here that would say, okay, well, if these were just the regular p orbitals, no hybridization going on, these should be approximately 90 degrees. All right, these are not close to 90 degrees. They're much closer to my ideal tetrahedral 109.5. Also, what we notice right here is that every time I add a lone pair, this shrinks the bond angles down. And this is a very important point. And actually, we can see this in another molecule as well. So if I look here at my boron trifluoride and nitrogen dioxide, okay, the bond angle in this one is 120 degrees. Bond angle over here is 115 degrees. And by the way, both of these are going to be Sp2 hybrids. And all of these up here were Sp3 hybrids. Okay? Because here, if we just look at this, this is attached to 3 things, right? Sp3. This is attached to 2 things and an electron pair up here. So that's, again, 3 things. So that's going to be an Sp2 hybrid. So this is our really important thing here. All right, so this is the important part right here, is that lone pairs reduce the bond angle. So if we have the atom here and there's no lone pairs on that central atom, it's going to be like the 120 degrees or the 109.5. But as soon as we start replacing atoms by lone pairs, they start shrinking, right? So 1 lone pair shrinks it down by about 2.5 degrees. We have 2 lone pairs, that shrinks the bond down by another 2.5 degrees. Over here, there's no lone pairs, 120 degrees. Then for this one, we have 1 lone pair, and that reduces it by about, 5 degrees or so. Now you might notice right here that, for instance, this nitrogen over here is an Sp3 hybrid. This nitrogen over here is an Sp2 hybrid, right? So how did we get from up here, which we talked about earlier, that here's my nitrogen, is doing this hybridization and it's going to an Sp3. Why did this one go to an Sp3, but why is this one only an Sp2? Well, the reason for this is basically partial hybridization. So when that happens, you basically don't hybridize all of the orbitals in there. All right, so basically just to explain this, again, we're just going to start off with our base nitrogen atom here. Okay, so that's just our base atom. But now, instead of hybridizing all of these like we did before, we're only going to hybridize part of them. So in other words, we're just going to hybridize only these guys right here. And we're just going to leave this last p electron alone. So what we're going to get here, and now notice I have here 1, 2, 3, 4, and then this p electron's going to be left alone. What we notice here is that we're going to have this part right there is going to be my lone pair. All right, and this is what we see right here. So that's that same lone pair, right? And meanwhile, here's my 2 bonds, right? There's my 2 bonds. And now this extra p orbital right here, this is actually going to help form a pi bond, okay? So right here, these are bonding to the 2 oxygens, and this extra one over here is going to be bonding to the extra oxygen in this case. So to explain what's actually kind of going on here, here's going to be my nitrogen, and here's going to be an oxygen, and these are going to be basically forming these bonds like so. There's also going to be this one up here. Okay, so this right here, this is my lone pair, and then these are going to be what's termed sigma bonds. So these are these sigma bonds, and these are what we're seeing right here. Okay, so these 2 electrons in this case are going to be forming the sigma bonds. Now this extra p electron that's up here is actually going to be going basically above and below there, right? Because remember, our p electrons look like little dumbbells right there. So here's my little p electron over here. This is above and below the nitrogen. And there's also going to be equivalent one on the oxygen as well. There's this unhybridized p orbital like so. And what's going to happen is there's going to be overlap between these 2 pi bonds like this, and well, the 2 p orbitals, and this is actually going to form what's known as a pi bond. So this one right here, this forms a pi bond. Here are some better graphics than my crappy drawing. Here we are looking at a molecule of formaldehyde. We have a carbon and an oxygen atom. The carbon has been sp2 hybridized, and you can see the 3 yellow sp2 lobes. Notice they are arranged on the plane. The blue unhybridized p orbital is above and below the plane. Next to it we have an oxygen atom, also sp2 hybridized, with the unhybridized p orbital in the same way. Now, when we combine with the 2 extra hydrogen atoms, which are just in the 1s state, we form a sigma bond between the carbon and each of the hydrogens, and then the p orbitals overlap on the top and bottom, forming a pi bond. The other sp2 orbitals on the oxygen have pairs of electrons in them, and they are going to be the 2 lone pairs. Now, even though it may look like there are 2 pi bonds, there is only one. Pi bonds always come in pairs, top and bottom or front and back. It's just like how you have a right hand and a left hand. So, your hands come in pairs, pi bonds come in pairs. Here is a molecule of acetylene. In this case, both carbons are going to be sp hybridized. The yellow sp orbitals lie in the plane, and we have 2 unhybridized p orbitals. One of the p orbitals is going above and below the plane, like before, and another is going to be in the plane, but going to the right and to the left of the carbon atom. The sp orbitals form a sigma bond between the carbon atoms, and also between the carbon and each hydrogen atom. And the 2 pairs of p orbitals form 2 pi bonds. One pi bond is going to be above and below the plane, and the other pi bond is going to be to the right and to the left of the carbon atoms in the plane. In total, we have 3 sigma bonds and 2 pi bonds. Next, we have the diatomic nitrogen molecule. Again, this is going to be sp hybridized. The p orbitals arrange themselves in the same way as they did for acetylene, and the other sp orbital in this case has an unpaired electron in it. Again, we have 1 sigma bond and 2 pi bonds. Finally, we have carbon dioxide. In this case, the central atom is going to be sp hybridized, and the outer oxygens are going to be sp2 hybridized. The outside orbitals have the unpaired electrons in them, and notice all the sp2 orbitals lie in the same plane. The pi orbitals are going to be oriented 90 degrees relative to one another and are above and below the plane, and to the right and to the left of the carbon and oxygen sigma bond in the other plane. There are going to be 2 sigma bonds and 2 pi bonds. Alright, so when we're dealing with our hybrid orbitals here, so every first bond in a molecule is going to be a sigma bond. So no matter what happens, even if you have double or triple bonds, you're always going to have a sigma bond there. If you have a double bond, you'll have 1 sigma and 1 pi. If you have a triple bond, you will have 1 sigma and 2 pi. All right. So for right here, if I have a nitrogen bond, that's just 1 sigma bond. Nitrogen double bond, that's going to be 1 sigma and 1 pi bond, and a triple bond, it's going to be 1 sigma and 2 pi bonds. Okay, so that's essentially what we're doing. So each one of these has a sigma bond, but then that extra one's a pi bond, and then I have 2 pi bonds. So if I were to look here at this molecule, so here I have this molecule. This would apparently just be called like cyanoformic acid, although as I look it up, it apparently doesn't exist or is too unstable to actually be synthesized, but either way, it's good for our purposes here. If we just want to find out how many sigma and pi bonds are in here, well, we can just start counting. So right here, since I have a triple bond, there's going to be 1 sigma and 2 pi bonds. This one here is just going to have 1 sigma bond. This one over here, that's just 1 sigma. That's also 1 sigma. And in here, it's going to be 1 sigma and 1 pi. So if I count through here, there's 1, 2, 3, 4, 5 sigmas, and 1, 2, 3 pi bonds. Okay, so that's just the basis of that. Alright, now as for the elements which can have expanded octets, we can also look at how their orbitals actually look. So remember we said before that elements up to neon can't do any expanded octets, but the elements below there can. And that's because they can access their neighboring 3D or 4D or 5D orbitals with them. So when we have those, for instance, we're going to look here at phosphorus. So, and this is going to be like for a compound like phosphorus pentachloride, PCl5. So we're going to be starting off, basically we'll just have here the neon core because I don't feel like drawing out the 1s and the 2s and the 2p electrons. So that's just my neon core, doesn't participate in anything anyway, so we can just write as the core electrons. Then I'm going to have here my 3s electrons, and then we're going to have my 3p, and then above there we're going to have the 3d electrons. Right. Okay, and when we fill up the phosphorus, remember that phosphorus is directly under the nitrogen, so it's going to have a similar electron configuration to nitrogen. So in this case, we actually need 5 open spots. Now, if I were to just go here and merge these, I would only get 4 from the sp3. So what I need to do is actually just borrow one of these d orbitals. So I don't have to hybridize the entire thing. I can just hybridize what I actually need. So when we do this, we're going to get here still my neon core, that's unchanged. But now we're going to get 5 spots, and then the rest of the d orbitals are just going to be up here. And this is going to be my sp3d. All right, so again, notice here I had 1, 2, 3, 4, 5, so this is just going to fill up like so. And then this can go and bond with the 5 chlorine atoms and, you know, form a happy little molecule. All right, and then unsurprisingly, we'll also just look at something which can form an sp3d2, and that would be something like sulfur with sulfur hexafluoride, or Sf6. Right, remember, sulfur is just right below the oxygen, so it's going to have a similar valence electron configuration. So again, we're just going to draw something pretty similar to this one up here. All right, so again, this is my sulfur in the ground state, and what I'm going to do is actually just borrow 2 of these d electron spaces to basically hybridize all these orbitals, and we're going to get still our neon core, but now 6 spots, and then 3 ds, which are just going to be left up here. And notice here I have 1, 2, 3, 4, 5, 6, so that's just going to fill them up like so. And this is going to be my sp3d2, because notice I took 1 of the s's, 3 of the p's, and 2 of the d's, and that's exactly where that name comes from. All right, and now I have 6 open spots. I can react with my 6 fluorines and make another happy little molecule. All right, so this chart here is on D2L, so you can go print it out and refer to it as we're going through this, make little notes. Now I'm going to give you a version of this chart, basically the same thing, except for the parts where I've already made little annotations on there. So for instance, the SP, SP2, SP3, SP3D, SP3D2, all that will be taken off. The little circled parts here on what things are polar and nonpolar, I'll take that off. But basically you'll have there, you know, the basic orientation and you know, what the base molecule looks like, so you have something to refer to when you're trying to match up your Lewis structures to the shape of the molecule in 3-dimensional space here. All right, so first up, just notice right here, everything in these rows, as we go along here, have the same hybridization. So everything here, and just the one thing, is going to be sp. This is sp2, this is sp3, this is sp3d, this is sp3d2, and then down here there's an sp3d3, where actually we're bonded to 7 things. That's a pretty uncommon one. We're never going to really encounter it, but when I got this little chart from wherever, that was just included, so it looks pretty. Now, what you of course notice if you start looking at this, all the X's represent the atom surrounding our central atom, which is A. And then of course right here, as you can see, these little lone pairs of electrons shooting out the sides like this. Okay, so you'll notice right here, these all have those same steric numbers that we referred to earlier. Okay, so remember our steric numbers were referred to. So steric number of 2 was sp, that's because it's bonded to 2 things. Steric number of 3 was sp2 because it's bonded to 3 things or in lone pairs. So there's 1, 2, 3, here's 1, 2, 3. Steric number of 4 is bonded to 4 things. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Over here, everything in here is bonded to 5 things. So there's 1, 2, 3, 4, 5. These are of course bonded to 5 things or 4 things in an electron pair. Here's 3 things and 2 electron pairs. Here's 2 things and 3 electron pairs, just like that. And then down here, everything is bonded to 6 things in electron pairs. So this is 6 separate atoms. There's 5 atoms in a lone pair. Here's 4 atoms and 2 lone pairs, 3 atoms and 3 lone pairs, and then just 2 atoms and 2 lone pairs for those. And then down here, those are just all bonded. The things I just want to refer to is, of course, the shapes. So right here, if we're dealing with an sp, these are just going to be nice and linear. There's no lone pairs on your central atom. That's just going to be a nice linear molecule. All right, and actually in the last video with the Lewis structures, we did see this. So right here is my carbon dioxide. The CO2, this will actually wind up being an sp hybrid, okay? Because there are no lone pairs on my central atom. So this is just going to be an sp hybrid, and just like we saw earlier, this would have 2 sigma bonds and 2 pi bonds. So this is just going to be an sp hybrid here for this carbon. So that's going to be sp. Here, this is an sp2. We just saw that one earlier today here. So of course, this is when we're bonded to 3 things, and they're identical, or just 2 things in a lone pair like that. All right, and just notice here the angle. So of course, if we're linear, this is going to be 180 degrees, and it'll probably be a little bit easier to see if you refer to your sheet there. Then of course, if we're looking at something which is 3 equivalent things, that's 120 degrees. All right, think about it. A circle is 360 degrees. Equivalently divided, that's going to be 120. 360 over 3 is 120. And then of course, if I go over here, I basically have my lone pair and 2 atoms. And this is going to be just a tad below 120 degrees. And we actually saw that earlier with the nitrogen dioxide, which was about 115 degrees like that. Then down here, of course, is my methane-like molecules, the tetrahedral ones, and we saw how we actually derived this 109.5 back in the organic structure video. Then down here, again, this is one that we saw, like the ammonia-type molecules. Right here, this is 107 degrees, and they might differ a little bit. They'll just be a little bit below 109. And then, of course, if I have a bent one with two things on it, that's, of course, going to be my water molecule. And, of course, we did the water molecule, over here. Remember, there's those two lone pairs. So this is going to be a 104.5. This is going to be an Sp3 hybrid, like we saw earlier. And then down here, this is where we start getting into the expanded octets, and things get a little bit weirder. So we saw this one down here earlier when we were doing the phosphorus pentachloride, because here's my phosphorus surrounded by 5 chlorine atoms, and of course, remember, we did that hybridization, found out that's going to be an Sp3 hybrid. So we have this type of molecule right here. All right, and then if we look at the bond angles for this, around the center is going to be 120 degrees, just like up here. You're 120 degrees, so this is going to be equatorial. Around the middle of the molecule is going to be 120 degrees, and above and below there, these are going to be 90 degrees relative to your equator. So these are going to basically be at the poles, and these 3 atoms are going to be on the equator. All right, then of course you can replace one of these atoms by a lone pair, and again, the angles are going to be a little bit different, so they're going to be squeezed in just a tad below 90 degrees now, and then these are going to be just a tad below 120 degrees, but pretty much equivalent, and this is going to be what they call either a sawhorse or a seesaw type configuration. All right, and then we can go and remove 2 of these, and we actually get a T-shaped configuration. So we have here 3 types of atoms, or atoms like this, a little less than 90 degrees over here, and we'll have these 2 lone pairs sticking out to the side. And then on this side, we'll have basically removed the 3 along the equator, and we'll just have the 2 atoms on the top and bottom here, and these will be at 180 degrees relative to each other because all the electron pairs are along the equator, so they're basically pushing on the atoms equivalently on the top and the bottom. Now you might say, well, why does it have to, why couldn't the atoms be at 90 degrees and put your lone pairs there? It just minimizes the energy, and that's, of course, where all atoms want to be at their minimum energy. So here we have our Sp3d2. All these have 6 atoms or pairs of electrons around there. So this one is going to be an octahedral type of configuration. So notice right here, basically these 4 atoms along the equator are forming a nice little square. So these are all going to be 90 degrees relative to one another. Then we also have 2 atoms on the top and the bottom, which are again at 90 degrees relative to each other. And we saw that when we did the sulfur hexafluoride out here. All right, then here we have the square pyramidal one. So here this is going to be 4 atoms along the equator, and then 1 going up towards the pole with my other electron pair at the pole here. And this looks like a nice little square pyramid, right? So there's my square part on the bottom and sticking up, so it looks like the little pyramids in Egypt that you'd see. Then here, if I have 2 lone pairs, well then the lone pairs will form along the poles of the atom, and I will get a square planar molecule. So these 4 atoms are going to be along the equator, and then my 2 lone pairs above and below there, and these will actually be at 90 degrees because it's they're being equally pushed on both sides, top and bottom, by the lone pairs. And here I have a T-shape, which is close to this one over here. Again, these are going to be a little less than 90 degrees, but now in this case I have 3 lone pairs of electrons shooting out here. And then finally, for this one, this is going to be a nice little linear one where we have the top and bottom atom here with the 4 lone pairs around the equator like so. And again, all these have the same hybridization here. All right, and then this one we're not going to worry about. Now, one other thing here that you'll notice that I've written up here is that the circled ones are polar. So all this stuff here is going to be polar. Non-circled ones are nonpolar, meaning they have no net dipole moment. And this is also assuming all the X atoms, all your outside atoms, are the same. If your X's are different, in other words, if you have like one of these things is a chlorine and the other one's a hydrogen or a fluorine or some other things there, that ruins the symmetry, and you are going to have a polar molecule. So this is, assuming that all the atoms on the outside are identical. If one or more of them are different, you lose the symmetry and you are going to have a polar molecule. So symmetry is extremely important when we're talking about dipole moments because you want everything pulling equally in all directions. If it doesn't happen, you have a dipole moment that happens. So if you look at why these are nonpolar, well here, this one, here's my A, the X is pulling equally in both directions, so it's going to be nonpolar. My trigonal planar one, here, they're basically pulling in all 3 directions. So think about a little tug of war, and you're standing in the middle, and you have one team pulling you up to the north, other one pulling you to the southwest and another one pulling you to the southeast, they're going to be pulling equivalently. You don't actually move in that kind of a case. Over here, my tetrahedral, well, now we're basically pulling, in all four directions equally in 3 dimensions. That's going to be, nice and nonpolar again. This one, the Trigonal Bipyramidal, is actually pretty easy to understand, because if you remember, this one was nonpolar. So all we're doing in this case, we still have that same kind of configuration around the equator. Now we just have somebody pulling on the top, equally pulling down on the bottom. Again, it's going to be nonpolar. And then down here, well, in this case, we have 4 pulling on you, nice and equivalently, and then also one on the top and one on the bottom, pulling at you equivalently. So this is also going to be nonpolar. And by the way, this guy down here would also be nonpolar as well. All of these, notice we've lost our symmetry, right? We have the atoms pulling in one direction, but then the electron pair pulling slightly differently in the other direction. And because we've lost that nice symmetry, we are now going to have a polar molecule. So here, these 2 atoms are pulling up, not as much as my electron pair, so that's going to cause a bit of a difference here. Notice here all my atoms are pulling down. I have my electron pair here on the top, so that's why this trigonal pyramidal one, like in ammonia, is going to be a polar molecule. In the seesaw configuration, well, notice all my atoms are over here on this side pulling, and I have this electron over on this side, so that's going to ruin my symmetry, going to have a polar molecule. And over here, you have all your atoms on the top, your electron pair on the bottom. Again, for your square pyramidal, going to be a polar molecule. So because you have that symmetry that's been lost, you wind up with polar molecules. And same thing over here. Notice we have 2 electron pairs pulling up, these atoms pulling down, so that's going to be non-symmetric. We have a polar molecule. Over here again, we have all the atoms on this side. We have the 2 pairs of electrons pulling this way, again a polar molecule. Now this one you might be saying, well, everything else is polar, why is this one nonpolar? Well, look at it. We have all the atoms around the equator pulling equivalently, then we have a pair of electrons on the top and on the bottom pulling equally, basically in the opposite directions. So because these are, this has this nice symmetry, these atoms are pulling that way, this pulls that way, that pulls that way, they all basically cancel each other out and you wind up with a nonpolar molecule. Over here, for my linear ones, again, here we have a linear configuration, just like we had over here, right? So it doesn't matter that I have electron pairs around the middle, because these are being pulled equally in both directions, so this basically just winds up to be a nonpolar molecule. Same thing over here. This is also linear, even though it has these 4 electron pairs around the equator, but they all pull equally, these all pull equally, everything cancels out, we have a nonpolar molecule. And then down here, this is another T-shaped one, just like this. Here was our atoms on this side, electron pairs going that way. So this T-shaped, are both going to be polar molecules. All right, so if we just look at some of the molecules that we did earlier, so what are their hybridization and everything going to be? Well, here we basically saw, the water already. So here, this water, this is going to be the bent configuration over here, and that's of course going to be an Sp3. So this is going to be an Sp3, and that's bent. The CO2, we just saw that earlier, which is up here. That's going to be an Sp and linear. All right, for that one. Carbon monoxide. This one is just going to be an Sp again, since both of these right here are diatomic, by definition they are always going to be linear, okay, because 2 points make a line, so these are always going to be linear. But here we just have the one bond, so that would really just kind of be like an Sp linear thing, although usually you really don't care too much about these. So here you remember our nitrous oxide that we did. Again, there's no lone pairs on this central atom, no matter which resonance structure we actually do end up with. So because of that, the nitrous oxide is going to be linear since there's no lone pairs on this. So this is going to be an Sp linear. Here for my ozone, and notice I kind of was saying this was going to happen because I drew it bent. Notice here I have a lone pair of electrons on there and 2 things it's bonded to. So this is going to be an Sp2, because there's 1, 2, 3, and this one is going to be in the bent configuration. And here we did see the methane, of course, that's just going to be your regular tetrahedral. The ammonia, right here, this is going to be my trigonal pyramidal. And water, we already saw that one. Right here, the Bf3, this one is going to be trigonal planar because there are no lone pairs on the central boron atom. Here, this one that we already saw, that's of course going to be my bent configuration. And then here for my thiocyanate ones and my cyanate that we saw, notice both of these carbons here don't have any lone pairs on them, so that means both of these would be linear and they would both be sp. The nitrogen monoxide. This one, yeah, there's, this is obviously just going to be linear because it's just diatomic, although it's hard to tell what the hybridization is going to be because we have this free radical thing here, so that kind of messes stuff up. And the Vesper model doesn't really work that well when we're talking about free radicals. And like I was saying here, this thing with the Vesper model and the free radicals doesn't really work that well. This one, would probably be somewhere between, this is where it gets weird, is between the Sp2 and Sp3. So it's somewhere in that vicinity. It's very difficult, because the model just isn't set up to deal with valence, these extra valence electrons. The actual bond angle for this, so this is actually how the molecule looks over here, is the chlorine with the oxygen like this. And the bond angle in there is about 117 degrees. So this 117 degrees is pretty consistent with what we saw earlier with the Sp2 hybridization. So it's probably pretty close to being more an Sp2 hybrid than the Sp3, even with that extra little electron. But don't worry, I'm not going to give you any tricky ones with radicals and asking you to figure out what the hybridization is like that, because they're really the model isn't just set up for those kind of things. All right, and then down here, notice here for my nitrate that we were doing. So again, my nitrogen doesn't have any lone pairs on it. It's just bonded to 3 things in there. So of course, when we do that, that's just going to be an Sp2 hybrid, and this is going to be Trigonal Planar. So just like this one right here. So anyway, I will end this here, and then the next video we'll just go through some more examples with expanded octets and going through the atoms and everything for those.